Okay, so hello. So this is the second part of the tutorial. So the setting that we'll talk about in this second part, as before, we have a set M of little m indivisible items. Think of them as goods, as having a positive value. Later, we'll also discuss chores here of items of negative value. We have n agents. As before, each agent has a monotone valuation function vi. A special case is that of additive valuations, which occupied most of the previous talk. Here we are specifically also interested in valuations which are not additive. And the new aspect here is that each agent I has an individual non-negative entitlement bi. Not all agents have the same entitlement. Like in the previous hour, it was equal entitlement. So you could say each agent had entitlement 1 over n. So now we change this, and each agent can have an individual entitlement. We call this arbitrary entitlements, which can possibly be non-equal. So how do we interpret this entitlement? So first of all, if we're talking about goods, so it's monotone. So the higher the entitlement is, it is better. You're entitled to receive more. And we also assume that it has a quantitative interpretation, that it's measured in some linear scale. One way of thinking of it is like if some agent J transfers her entitlement to an agent I, then the new entitlement of agent I is the sum of the two entitlements. And we also assume that entitlements sum up to 1. So this indicates that the agents collectively are entitled to receive all the goods, no less and no more. So examples where unequal entitlement may arise. So for one example would be allocation of seats in the parliament to political parties. The entitlements of each party would be the number of votes that it got in the elections. Dividing an inheritance among, let's say, a widow who's entitled maybe to half the inheritance, and let's say 2 children, each one would be entitled maybe to 1/4 of the inheritance. Handling student registration to courses of limited capacity. It could be, let's say, that third-year students have higher priority over second-year students. Another example would be the NBA draft. So that's allocation of eligible basketball players to NBA teams. And it's done via a procedure in which teams who had ended at lower positions in the previous season have higher entitlement. They choose first the new players that joined in the current year. So let's recall what we saw for equal entitlement. So we had some ideal fairness notions that they represent what we aspire to achieve. They were not always feasible, so sometimes we settled for approximations of them. And they came in 2 flavors. There were the share-based notions. So there was the maximum share for arbitrary valuations. And for specific share for additive valuations is the proportional share. It makes maybe a bit less sense for non-additive valuations. And there are also comparison-based notions in which an agent compares what she got to what other agents got. And here we have the notion of envy-freeness. So this was for equal entitlement. So what we'll present here is we want fairness notions that apply to arbitrary, possibly unequal entitlement, and arbitrary monotone valuations. We should not insist that valuations are additive. We will not discuss comparison-based notions such as envy-freeness here. And the main reason is because at least I'm not aware of a very good extension of envy-freeness to the case of unequal entitlement. So really, in a sense, there's nothing that I would like to present. And instead, we'll concentrate on share-based fairness notions. And we'll see 3 shares. So one is MMS hat. So that's a minimal upper bound on all feasible ex post shares, we'll see MES hat, maximum expectation share, which is a minimal upper bound on all feasible ex-ante shares. And we'll also see the any price share, APS, which is a share which is not meant to be an upper bound, really a share that you could possibly want to use in a sense that it passes a sanity check. It looks reasonable under some sanity check that I'll discuss. So these are the definitions presented in the talk. Later, we'll also mention some results. So what kind of ex-post share-based fairness notions we have? So recall an agent has an entitlement BI, which is non-negative. The sum of entitlements is 1. For equal entitlements, since there are n agents, each agent the entitlement would be 1 over n. So what should we do in the unequal entitlement case? So first, suppose that the entitlement of an agent is 1 over k or some integer k. In this case, it's reasonable to think that the agent would think as if is part of an allocation situation in which there are k equally entitled agents. So we might want to use the MMS in this case, but with respect to k agents. So the agent possible share value would be that the agent can partition all items into k bundles, not n bundles, in the way which is best possible for the agent, under the assumption that she will receive the worst of these bundles. So suppose that indeed this is what we do, that if the entitlement is 1 over an integer, we use the MMS with respect to this integer k as the share value. And the question is, in that case, what should the share value be when the entitlement is not 1 over an integer, but let's say between 1 over k and 1 over k plus 1. So what we choose to do here is optimistic rounding. So we just round up the entitlement of the agent from this fraction, which was between 1 over k plus 1 and 1 over k. We round it up to 1 over k. And then we take the MMS as if there were k agents. And this is the value of the share. And we call it MMS hat because we rounded up the entitlement. Why did we do that? What's the motivation? So the motivation for this is that this share is an upper bound on all possible feasible shares. Like the MMS was an upper bound on feasible shares in the case of equal entitlement, MMS hat is an upper bound for the case of unequal entitlement. So why is it an upper bound? Because there might be k agents, each exactly with entitlement BI, and exactly with the same valuation VI, and then at least one of the agents, whatever allocation we choose, will not be able to get more than MMS hat VI. So in this respect, it's an upper bound. Moreover, this upper bound is tight even with respect to nice feasible shares. So in work with Moshe, we show that there's a collection of shares such that each share is feasible. It's self-maximizing. We saw this concept in the previous part of the tutorial. And for every, so the shares are feasible, and for every entitlement BI, and for every, let's say, additive valuation VI, the value of at least one of these shares is equal to this MMS hat. So if you want to dominate all possible feasible shares, you have to be at least as large as MMS hat, and being of this value MMS hat is large enough. So this share is dominating. So another share that we'll discuss here, it was introduced in work with Moshe and Tomer, is the any price share. And this is now not an upper bound, but maybe a share that you actually would say is a reasonable share to use. So recall first that the MMS of an agent is the value that she is guaranteed to get when she plays a cutter in a cut and choose game. So at a high level, the APS of an agent is the value that she is guaranteed to get as a chooser, not a cutter, in a different game, a price and choose game. So price and choose is somewhat related to cut and choose, but the difference is that the operation of pricing can be done also in cases of unequal entitlement, whereas cut and choose makes sense only in the case of equal entitlement. So even if the entitlement is 1 over an integer, 1 over case for some integer k, the value of the any price share need not be equal to the value of the MMS. And the reason is because they're defined through different games. In one case, you're the cutter in cut and choose, and in the other case, you're a chooser in price and choose, and there's no reason that the two values would be the same. In fact, the APS would always be at least as large as the MMS, and sometimes larger. Okay, so now we reach a definition. So an adversary assigns a non-negative vector of prices to the items so that the prices sum up to 1. So this is the first, this is the price step of the price and choose game. And then the agent can pick any bundle as long as the price of this bundle does not exceed her entitlement. Okay, so in a sense, the adversary says how much each item is worth, and you're allowed to take as many items as you can, or as high value as you can, as long as you don't exceed what you can pay for with your entitlement. So the APS, the any price share, is the minimum over all possible prices of the maximum value bundle that you can pick under these prices. So this is a min-max sort of definition for the any price share. So like all shares, the APS of an agent depends only on the valuation function of the agent and the entitlement of the agent. It does not depend on the valuations of other agents and does not depend on the entitlements of other agents. So let's see an example. Suppose that we have an agent with an additive valuation, an entitlement 2/5, and suppose there are 5 items, the 2 blue ones of value 7 and the 3 smaller green ones, each of value 5. What would be the APS in this case? So we can give a price, the adversary can give prices of 0.23 for the large item and 0.18 for the small items. And now the agent can afford to buy either 1 large item or 2 small items. The agent cannot afford to buy, let's say, a large item and a small item. So the maximum value that she could get is 5 plus 5, in this case, which is 10. So this implies that the APS is at most 10. It doesn't imply that the APS is exactly 10, because maybe there's a different pricing scheme in which she cannot even afford to get items of value 10. So how do we prove that the APS is in fact exactly 10? So we can consider 5 bundles such that each item is in 2 of them. So the bundles are each time 2 consecutive items, and then the last bundle is E and A together. So no matter how you price the items, at least one bundle would have price 0.4, and then you'd be able to buy it. So no matter which price vector you give, you get that the agent can afford a bundle of value 10 at least. So the value of the APS is at least 10. So it's at most 10, at least 10, so it has to be exactly 10. This leads us to another definition of the APS. It's convenient to have 2 definitions for the APS, one to give upper bounds. The pricing definition gives an upper bound. So now the definition that gives also a lower bound on the value of the APS. So we say that the distribution over subsets of the items, that this distribution is BI balanced. So what is this distribution? For each subset, we associate a probability with which we pick this subset, and the probabilities sum up to 1. And this distribution is BI balanced if, when selecting a bundle at random from this distribution, each item has probability exactly BI of appearing in this random bundle. So as an example, in the previous example here, when I had these 5 bundles A, B, B, C, C, D, and so on, if I give each one of these bundles probability 1/5, then since each item is exactly in 2 bundles, each item would be selected with probability exactly 2 fit, which is BI. So this distribution would be BI balanced. So the max-min definition of the APS, which is equivalent to the definition of the pricing definition, equivalence goes through linear programming duality, is that the APS is the value of the worst bundle in the best BI balanced distribution. So the agent can choose the BI balanced distribution, and the worst bundle in this distribution is the value of the APS. We can compare it to the definition of the MMS in the case of equal entitlements. So the maximin share, the MMS, has exactly the same definition, except that the distribution has to be over disjoint bundles. You partition into n disjoint bundles, and you get the worst bundle, whereas in the APS, you're allowed to have overlapping bundles, but you have to give them weight in such a way that each item is on average in a BI fraction of the bundles. So because the APS is the relaxed version of the maximin shares, then even in the case of equal entitlement, the APS is always at least as large as the MMS. And in fact, sometimes it is strictly larger. So we introduce here a definition for a share-based notion. How do we convince ourselves that this is a reasonable definition? So here's a sanity check that we can do. Consider dividing a homogeneous divisible good. So what's a homogeneous divisible good? Something like water. All you care, for example, is how much water you get. You don't care if you get it from the left-hand side of the pool or the right-hand side of the pool, or money. So we can model a large homogeneous divisible good as many identical items. So think of M for very large M, $100 bills. For very large M, a big pile of money. And it's divisible. You can divide it to arbitrarily small parts. So in this case, how would we allocate it among agents of unequal entitlement? Suppose there's an inheritance of $1 million. The widow is entitled to half, and each of the 2 children to 1/4. What would we give each one? So I think the most reasonable thing is a proportional allocation. The widow would get half with $1 million, and each of the children 1/4, just according to their entitlements. The number of identical items that they get is just BI, their entitlement, times the total number of items that there is. And we would not even ask them what their valuation function is. So let's say if you want to divide water equally, you don't start asking them how much is 1 gallon of water worth for you, maybe how much is 2 gallons of water worth to you. Is it twice as much as 1 gallon, or maybe not twice as much? You don't even ask this. This is the allocation that you do. So in a sense, it's not a theorem, but we assume that this is a reasonable allocation to do in the case that you have a homogeneous divisible good. And indeed, in the equal entitlement case, if we look at the ideal fairness notion, the MMS, the proportional share for additive valuations, and the free allocation, all are satisfied by the proportional allocation. So now let's ask whether the APS satisfies it. So we claim that indeed the APS value for an agent I is the value that she assigns, so the APS is the value, to exactly BI times M items. So exactly what you would get by the proportional allocation. So how do we see that this is an upper bound on the APS? You can price each one of the items at 1/M, and she can afford to buy only BI times M items. So it's not larger than that. And how do we see that it's not smaller than that? For that, we go to the alternative definition through the BI balance distribution. So suppose, let's say that BI times M is 5. Maybe she's entitled, like it's 5 items. So we can partition the bundle, all the set of items into M overlapping sets, each with 5 items, such that each item is exactly in 5 sets, and give a probability of 1 over m to each one of these bundles. So under this probability, this is a balanced distribution. So every item is selected exactly with probability bi. And each one of these bundles is worth exactly bi times m. So each one has value for her, like a value of a bundle of bi times m items. So indeed, what we see is when we divide the homogeneous divisible good, the APS, the proportional allocation, is an APS allocation. And it doesn't matter what the valuations of the agents are. And if the valuations are strictly monotone, then the proportional allocation, in fact, is the only APS allocation. If they're not strictly monotone, for example, somebody has a valuation which is identically 0, maybe you don't need to give this agent anything, and then you can have additional allocations. But if it's strictly monotone, then it's the only allocation. The proportional allocation is the only APS allocation. So in this respect, the APS passes our sanity check. So now let's talk about ex ante fairness. So that's if you look at randomized allocation, the expected value that you receive. So in this case, if you give each agent the grant bundle, all the items, with probability exactly equal to her entitlement, then she gets her proportional share, bi times the value of the grant bundle. She gets it in expectation. With some probability she gets 0, with some probability she gets everything, and in expectation this is what she gets. And this is the optimal guarantee that you can give if valuations are additive, and indeed the proportional share is a good share in the case of additive valuations. But if valuations are not additive, let's say they are concave or sub-additive, submodular for discrete items, then typically the sum of values, if I partition things into many parts, I increase the value. The sum of values of parts is higher than the value of the whole. So think of their, let's say, having n identical items, where each agent just wants to receive one item and any additional item is just a substitute, doesn't help. Then the agents would want each agent to receive one item and not one agent to receive all the items and all the rest to receive 0. So this ex ante fairness, the proportional share, even though it is feasible, it's not very useful if valuations are not additive. So what share is more useful? So we look at the maximum expectation share, and we can recall before the notion of the BI balance distribution, a distribution over sets in which every item appears with the random set with probability BI. And recall that the APS is the value of the worst bundle in the best distribution, BI balance distribution. So the MES, the maximum expected share, is the expected share value of a random bundle. You think of a random allocation of these subsets, not that you get the worst one, and then you get the random bundle. So it's the expected value of a random bundle in the best BI balance distribution. So it's clear that the MES is at least as large as the APS because you get a random bundle and not the worst bundle. And also it's at least as large as the proportional share because a valid distribution is to say the grant bundle having all the items is one subset, which you get it with probability BI. And the empty bundle is another subset, which you get with probability 0, and this is a balanced distribution. So it's always at least as large as the proportional share and at least as large as the APS. And if we want a dominating ex ante share, that you cannot possibly give anything better than this in a feasible ex ante share, then we do the same trick that we did as with the MMS. So recall the maximum expectation share is the expected value of the random bundle in the best PI balance distribution. So recall the notion of rounding up your entitlement to 1 over an integer. So you round it to 1 over k. So the MES hat is the expected value of a random bundle in the best BI hat balance distribution. And the advantage of this share is that it's an upper bound on every feasible ex ante share. You cannot think of any feasible ex ante share that has higher value than this. Okay, so summary of share-based notions. So the interesting case was that entitlement could be something which is not 1 over an integer. So we have these upper bounds on feasible shares. So we had the MMS hat as an ex post notion, and then maximum expectation share hat as an ex ante notion. And we also have not upper bounds, but actual shares that have nice properties. So the any price share is a share that induces the proportional allocation for dividing divisible homogeneous good. And the proportional share is a share that ex ante is always feasible. Okay, so far we introduced the fairness notions that we are going to consider, and now we'll discuss some results. So are there any questions about the fairness notions?
Yeah, I have a question. So how is MMS hat related to the pessimistic share? Because that seems to have a similar definition.
So there is a different share instead of MMS hat that we rounded up the entitlement. One thing you can think is like a pessimistic version to round down. Is that what you mean? And the pessimistic share also allows you to take other fractions. Is that what
Yeah,
you are referring to?
yeah, that's what I, yeah.
Yes, so, okay, so there is this alternative. Let's think of the simplest alternative, just round down to 1 over an integer. And the advantage of this might be that you think that maybe this share would be feasible, at least in the case where all agents have the same valuation function. So the point is that with unequal entitlement, even if all agents have the same valuation function, and even if it is additive, this share is not feasible anymore. You can have examples when it's not feasible. So maybe the main reason to consider it, I think, was because it was feasible in interesting cases, but even if it doesn't have this property, so why not round up instead of down and be more ambitious? So that by rounding up, you know that you cannot do any better than that with MMS hat. It's like optimal in some sense. Rounding down, it's just some share in the middle, like doing nothing, in a sense. The APS, in a sense, is a strengthening of this pessimistic share. So a significant one maybe, but so if you want something in the middle, I think the APS is a better choice.
Yeah. Okay.
But it's of course a matter of opinion. Yeah. Okay. So what we'll consider now is we'll move to additive valuations and consider to what extent we can find allocations that give us some fraction of the share. Okay. So neither the APS nor MMS hat nor MES hat are feasible for additive valuations. What approximation can we give? So let's start with the easiest case. This is the ex ante approximation of the MES hat. So recall that for additive valuation, the MES is simply the proportional share. It's exactly the same for additive. So the MES is feasible. You can give each agent the grand bundle with probability BI, or if you are additive, as we are here, each item separately you can give with probability BI. So the problem with MES hat is that after rounding up the entitlement, the sum of entitlements exceeds 1. So this is really the problem with it, and because of this, it is not feasible. So by how much can it exceed 1? So you can prove that there's a certain constant gamma such that it can exceed 1 at most the ratio of gamma, which is around 1.69. So what might happen? Might happen that one agent had entitlement half plus epsilon, and this was rounded up to 1, and another had entitlement 1/3 plus epsilon, this was rounded up to half, and so on. So what you can do, instead of giving each agent 1 over each item with probability BI, you can give each agent I, let's say each item with probability BI hat divided by the sum of these bj hats. So this sum is never larger than gamma. And if you do that, of course, you allocate all the items. So because the sum of bij's is never larger than gamma, the approximation ratio is always at least as good as 0.591. And this is like the best guarantee that you can guarantee in the worst case. So understanding what you can do ex ante is pretty simple. The more difficult case is what you can do ex post. So of course, the same argument shows that you cannot get a ratio better than 1 over gamma because of the rounding up of the entitlements when you look at MMS hat. But in fact, you cannot get even a ratio better than 1/2. And here's an example. So suppose that M, the number of items, is 2n minus 2, and they're all of equal value. And there are n minus 1 agents of entitlement slightly larger than 1 over n, but smaller than 1 over n minus 1. So you round up their entitlement to 1 over n minus 1. And then each one of them thinks that their MMS is, since there are 2n minus 2n items, each one of them thinks that their MMS is 2. So they think they're entitled to 2 items, ex post. The other agent has entitlement slightly smaller than 1 over n. So after rounding it up, okay, it's let's say 1 over n. But so its MMS hat is 1. So it believes it is entitled at least to 1 item. So altogether, they believe that they're entitled to 2n minus 1 items, and there are only 2n minus 2 items. So one agent will not get what is entitled to, and if it's it's the last agent has to get at least 1 item at least, otherwise there's no approximation of the MMS set. So at least 1 agent gets no more than half the MMS set. So you cannot do better than that. So the interesting thing is that that indeed for every allocation instance with arbitrary entitlements and additive valuation, there is indeed a half MMS set allocation. You can achieve that. So what we can prove is an existential result that such an allocation exists. And if you want a polynomial time algorithm to compute such an allocation, you can approximate it. You can get half minus epsilon MMS and compute it in polynomial time, MMS hat. And this is quite interesting because let's say for MMS, we don't know what the best approximation ratio is, but for MMS hat, we do. So the technique in which we use in order to prove this is a bidding game, which was introduced in the same paper that introduced the any price share. And it proceeds as follows. So it's a game for allocating the M items to the N agents, and the game takes M rounds. In each round, we allocate 1 item. So initially, each agent gets a budget equal to her entitlement. So this game is tailored to the situation where agents might have different entitlements, and this is reflected by the fact that they have different budgets. And in every round, each agent makes a bid not higher than her remaining budget. The agent can choose which bid to make as long as it doesn't exceed her budget. The higher bidder wins the round. We don't care how ties are broken for the sake of analysis, but say they're broken at random. She pays her bid, so this is deducted from her budget, and then she gets to pick an item of her choice. After she picks the item, the round ends, and we get to the new round. Again, they submit bids, the winner picks an item, and so on. And the game ends when no items are left. It could also end when no budget is left, but there's no reason for no budget to be left because the last agent to have some budget left can win all the remaining items by bidding some small epsilon in each round and winning all the rounds. So you can assume that all items are consumed. So the proof techniques by which we use to prove that half MMS hat allocations exist is to consider this bidding game and design safe strategies for the game. So what are these strategies? They tell the agents how to bid, given their budget and the budgets remaining to other agents and the items that are left, and which items to choose when they win the bid. And the safe strategy is a strategy that ensures that no matter what strategies are used by the other agent, the agent gets a value at the end of at least half MMS head. And once we design such safe strategies, this implies that half MMS head allocations exist because all agents can use such a safe strategy. If in addition the safe strategy can be implemented in polynomial time, then it would give a polynomial time algorithm to find the half MMS head allocation. But our strategy, we don't know how to implement it in polynomial time. So in general, the bidding game is very useful in obtaining results for unequal entitlement. It comes in several variations, and some results use variations of the game. One of them is, let's say, the winner of a round pays the second price, like use second price auctions per round instead of first price. Another option is that the winner chooses not just one item, but can choose maybe several items if she can afford to pay for all of them. And if we look at unequal entitlement, the strongest known approximations were proved by designing safe strategies for the bidding game. So the first such result was showing that you have 3/5 APS allocations for additive valuations. For submodular valuations, so you can have give each agent at least 1/3 of their APS. And what we discussed now, you can give half of MMS head. For additive valuation, in fact, half of a larger share of TPS head. That doesn't matter here what it means. It's some share which is larger than MMS head. And since this last result, MMS is tight, then its proof is somewhat different than the proofs of the earlier results. In the earlier results, we designed ad hoc strategies that achieve what we want. In the last results, because it is tight, we really need to design optimal strategies to achieve what we want. And this requires us to characterize how worst case optimal strategies look in the bidding game. So have some results in this direction as well as like a byproduct of this result. What about best of both worlds? So if we look at the MMS head ex post and MES head ex ante, we cannot have any constant approximation of them simultaneously. And here's a simple example. So suppose there are only 2 identical items and 3 agents, and the entitlements, 2 agents have entitlement slightly above 1/3 and one has slightly below 1/3. So those with entitlement slightly above 1/3 get their entitlement rounded up to half. So each one of them thinks she's entitled to 1 item in every ex post allocation. Otherwise, there's no approximation to her MMS head. Whereas agent 3, at least ex ante says, I should have positive probability of receiving an item because my entitlement is positive, is non-zero. Otherwise, there's no approximation of the MES, but you can never give her an item because the other agents need to get both items in every allocation. So the ex ante and ex post requirements are incompatible. You cannot achieve both of them simultaneously. Okay, any questions about this part? Okay, so summary for additive valuation. So ex post, we can ensure half of the MMS hat, and hence it's at least half of every feasible share. And this is best possible. Ex ante, we can ensure 0.591 of the MES hat, and hence at least this much of every feasible share ex ante. And again, this is best possible, but there is no best of both worlds result. We can have either one or the other, but not both. So now we'll move to chores. So chores, unlike goods, like they are items of negative values, or another way of thinking of them, the items of positive cost, things like doing the laundry, cleaning the bathroom, so on. And in these settings, like all chores must be assigned. And agents have, instead of entitlements, we can call it responsibilities, like what they are responsible, like to what extent they are responsible to doing these chores. Like it's not entitled to do this chore, they have to do it. So agents aim to minimize their costs. They want to do as little as possible. And the share, in this case, bounds the maximal cost that the agent might suffer. Like in the case of goods, it says what's the minimum value I should get. For chores, it's what's the maximal cost that I might suffer. And we can extend the fairness definition to chores. So max-min changes to minimax, like it's an end partition that minimizes the cost of the most costly bundle. If we want an ex post dominating share, then instead of rounding up the entitlement, let's say to 1 over k, we'd round down the responsibility to 1 over k plus 1. And similarly for an ex ante dominating share, the maximum expectation share. So I will not spend much time on it. It's fairly intuitive what you need to do when you consider chores instead of goods. So for chores, it turns out there is a best of both worlds result. So there is a polynomial time randomized assignment algorithm that for every input instance with additive cost functions and arbitrary responsibilities output the distribution of their assignments for which for every agent ex ante, the expected cost that he gets is at most her proportional share. And the proportional share is always at least at most twice as much as this MES share with the entitlement rounded down. And this is best possible guarantee that you can actually give. You cannot give a guarantee better than proportional share ex ante. And ex post, the cost is at most twice this MMS rounded down. And moreover, also here, the approximation ratio 2 is the best possible. You cannot do better than that. So we have a best possible result that even doesn't lose anything in the constants. Like the best approximation that you can get for the ex ante guarantees and the ex post guarantees, you can get them simultaneously. So proving this is done through a general technique that is worth knowing. It's applicable not just for allocation problem, it's used in scheduling, it's used in other situations. And we call it faithful implementation of fractional allocations. So the technique goes as follows. We design a fractional allocation, let's call it A star, with good fairness properties. So what is a fractional allocation? You can assign items fractionally to agents. So some agent can get, well, let's say, half of an item, and then some other agent can get the other half. And for additive valuations, there's a natural way of extending the evaluation function also to fractional allocation. If you get, let's say, 1/3 of an item, it's as if you got 1/3 of the value of the item. So you can extend the valuation function also to fractional allocations. So we find the fractional allocation with good fairness properties. So if we look at the value of this allocation to the agents, it's good according to our fairness criteria. Let's say it gives the maximin share or whatever. So a fractional allocation is not a legal allocation because we're not allowed to subdivide items. So an allocation is faithful with respect to this fractional allocation if it's an integral allocation in which every agent gets a value which is equal to the value that she gets in a fractional allocation up to one item. So like rounding the fractional allocation to an integer allocation, you needed somehow to round one item, like one agent, in a sense, got one item more or one item less than what the fractional value would dictate. And a faithful implementation of a fractional allocation is this distribution over these faithful allocations in which the expectation of the distribution is exactly the fractional allocation. So if we choose at random an allocation from this distribution, then the probability that we get a particular item is exactly the same as the fraction of the item that we held in the fractional allocation. So faithful implementations give best of both worlds type guarantees. So ex ante, every agent gets her fractional value in expectation. So whatever you get in the fractional allocation, you get ex ante in this distribution, in this faithful implementation. And ex post, you get the value up to one item. Now, value up to one item, if you are considering goods, and let's say you're entitled to get one good, getting the value up to one item is not so good because you might get one good minus one good, which is nothing. But for chores, value up to one item is pretty not that bad. If your responsibility is to do, let's say, 2 chores, and instead of, let's say, 1 chore, and instead of that you do 2, then you just doubled what you got. So it's an approximation ratio of 2. So this technique is very good when we want to have best of both worlds results for chores. We can also use it for goods, but it's more difficult to use it for goods. For chores, it's relatively straightforward how to use it. So the faithful implementation that we'll do will start with a proportional fractional allocation in which each agent gets a BI fraction of each item. So each agent I gets a BI fraction of each item. So in this allocation, each agent gets exactly her proportional share. So in a faithful implementation, ex ante, she'll also get exactly her proportional share. And ex post, she'll get her proportional share up to one item. And it takes some little computation to show that this is not more than twice her MMS, maximum share, even after rounding down her entitlement. So, and this is the best possible approximation ratio with respect to MMS rounded down. So, so this is the proof of the best of both worlds results. So as a summary, one question we can ask ourselves, so with develop a theory of fair allocations where we provide definitions, but and prove results, but somehow the end goal is to say, okay, which allocation mechanism would you like to use? And it appears to us maybe that the allocation mechanisms that we use in our proofs make sense also in practice. Okay, maybe yes, maybe not. So the positive results for goods was proved using the bidding game. And the bidding game, it looks to us as a plausible option of how to actually do allocations in practice. Like it looks like a fair procedure. Each agent gets a budget equal to her entitlement, so it satisfies what you expect from entitlements. And agents have safe strategies that guarantee that nothing catastrophic would happen. Like they can guarantee to them at least half of any feasible share, whatever share they can think of. So and they can get the best possible worst case guarantees this way. And maybe they can get even more. So it looks to us like a reasonable allocation mechanism. And for chores also, doing a faithful implementation of the proportional allocation gives the best worst case ex ante and ex post guarantees simultaneously. And let me add, in both cases, if you're interested in share-based notions, fairness, after the allocation, after you get an allocation from any one of these mechanisms, if you have Pareto improving moves, some agents want to exchange goods between them and improve the value of the bundles that they get, that's fine. In terms of share-based notion, they still keep their share guarantees. So you can think of these allocations sometimes as just an initial allocation, and later agents are free to make improving moves if they find ones. Let's say if they want eventually to reach a Pareto optimal allocation. So I'll end with some open questions. So the first one is a conceptual one. We discussed here share-based notions, and the reason why I did not discuss freeness-based notions is because I don't know of a good notion that passes the sanity check that we did before of dividing a homogeneous divisible good. So there are notions of weighted NV freeness, for example, that were introduced, but if you use them to divide a homogeneous good, when agents don't have additive valuations but other valuations, it does not give the proportional allocation. So it's not clear what a good notion of NV freeness would be in the case of unequal entitlement. So specific questions about additive valuations. So we said that the best approximation ratio known for max-min share allocations in the case of equal entitlement is something around 3/4. And we know that a ratio better than, let's say, 39/40, you cannot do better than that. But this is for small values of n, this upper bound. And we don't know what happens when n grows. And it's possible that for every epsilon, if the number of agents is large enough, you can always have a 1 minus epsilon MMS allocation. So an open question is this true or not? Another form of approximation is to ask what happens if the total entitlement of agents is slightly smaller than 1, not equal to 1. Maybe then shares become feasible. So for example, is the APS feasible if the sum of entitlements is smaller than 1? This we don't know. We can also ask this for the MMS rounded down, like with entitlements rounded down to 1 over an integer, whether this is feasible when the sum of the entitlements is smaller than 1. And the last open question is about what happens with non-additive valuations, let's say sub-additive valuations, other classes of valuations, but let's stick specifically to sub-additive valuations. We don't know if there's a constant approximation for the MMS in this case. We know that there's nothing better than half MMS, that there are examples in which you cannot get better than that, but maybe half MMS is the best approximation ratio that you can give. And that would be very interesting. It seems to both, like there are interesting combinatorial analogs of this question, which, so there's a lot of content here. And there's a possibility that maybe you can have, in fact, tight results here. For additive valuations, it seems to me hopeless that we'll ever know what the best approximation ratio for the MMS is. But maybe for sub-additive valuations, for XOS valuations, maybe the answer is simply half. And so in this respect, it's a good question because it might have a very nice answer with a very nice proof. Okay, so I will end here. So any questions?